Hi guys, welcome back to our channel. Today we'll be speaking about isotopes, what they are, how is it that we use them to calculate relative atomic mass, AR. Now when we speak of what an isotope is, what we are making mention of are atoms of the same element having the same atomic number, but the mass number is different. So what's important here is that we are looking at atoms of the same element. Mass number is atomic number is the same, while the mass number differs. Let's look at some examples. Let's take neon 20, which has mass number 20, neon 21, mass number 21, and we have neon 22 with mass number 22. Atomic number 10. So for each of these, we see that we're looking at the same element, neon. The mass number or mass numbers are different. We're looking at 20 versus 21 versus 22. Atomic number is the same. So we have 10 protons in each of these atoms of neon. When we subtract the atomic number from the mass number, we get the number of neutrons. So in neon 20 we have 10 neutrons, whereas in neon 21 we have 11 neutrons because that's 21 minus 10. Whereas in neon 22 we have 12 neutrons, which is 22 minus 10. Let's take, for example, protium, which is hydrogen 1 with mass number 1, deuterium, which is hydrogen 2 with mass number 2, and we have tritium, which is hydrogen 3. All these are examples of atoms of hydrogen, same atomic number 1, mass number different, therefore they are isotopes of hydrogen. This one having 0 neutrons, this one having 1 neutron, and this one having 2 neutrons. So always remember we're looking at atoms of the same element with same atomic number, but the mass number or the number of neutrons differ. Now, the isotopes of elements are used to determine what we call the relative atomic mass or the AR of an element. For the atoms of different elements, so the mass of a single atom is extremely small. So what we do is that we weigh it against a standard, and this standard is an atom of carbon 12, which has a mass of exactly 12.00 units. So when we look at the relative atomic mass, AR or RAM, what we're looking at is the weighted average mass of all the naturally occurring atoms of an element on a scale where an atom of carbon 12 has a mass of exactly 12.00 units. And in order to do this, we need one key piece of information in addition to the isotopes of the element. We need what we call the relative isotopic abundance, or the percentage abundance of each of the isotopes. On some periodic tables, when we look, we will see the mass numbers being decimals rather than whole numbers. The reason for this is that most of the naturally occurring elements, they exist as a mixture of isotopes, and the mass number will not be an exact value, so it's reported as a decimal because we are taking into consideration the proportion of each of the isotopes, or we're looking at the relative isotopic abundances of the isotopes of an element, of the element. If we look back at the example that I used, neon, so we have neon 20, we have neon 21, and we have neon 22. Naturally occurring neon exists as 90%, 90.9% neon 20, 0.30%, if we look at the example I just used with the neon, where we have naturally occurring neon existing as neon 20, which exists as 90.9% neon 20. We have neon 21, and the percentage abundance of neon 21 is 0.30%, and the percent abundance of neon 22 is 8.8%. So naturally occurring neon will exist as a mixture of these three isotopes. In relative abundance, 90.9% neon 20, 0.30% neon 21, and 8.8% neon 22. How is it that we use these values in order to calculate the relative atomic mass AR? AR, relative atomic mass, is equal to the sum of the masses of the isotopes multiplied by their relative abundances divided by 100, because relative abundance is out of 100%. If you add these values, you'll see that it will total 100%. So we're looking at the sum of the mass of the isotope multiplied by its relative abundance, which I'm going to write as RA, relative abundance, and this is all divided by 100. Let's use the values we have there. So the mass of neon 20, so the mass of the isotope 20 multiplied by its relative abundance 90.9 plus the mass of the other isotope, that's neon 21, mass 21, multiplied by its percentage abundance 0.30 plus the mass of neon 22 multiplied by its percentage abundance, that's 22, multiplied by 8.8. This will be all divided by 100, all over 100, since percentage abundance is out of 100%. And when we add those, we will get the value for the relative atomic mass of neon to be 20.2. So always remember that it's the sum of the mass of the isotopes multiplied by their relative abundance divided by 100. Let's look at one final example. Let's look at chlorine. Where chlorine exists as chlorine 35 and we have chlorine 37. In percentage abundance 75%. And for this one we have 25%. Now let's think about to work on the AR. It's gonna be the mass times percentage abundance, where we have mass 35 multiplied by its percentage abundance, .75 plus .37, which is the mass of the other isotope, multiplied by its percentage abundance, which is 25. And this is divided by 100. And when we work these values out, we will see that the relative atomic mass of chlorine is 35.5. Thanks for watching. Remember to like, share, and subscribe. Bye.